In this chapter, you will learn what is traveling longitudinal wave. First, one end of a stretched spring is held by the hand. Next, the hand vibrates or oscillates in a direction along the spring. We see that a series of compressions and wear fractions travel in a direction along the spring. We denote the compression by C and the wear fractions by R. Next, when a paper sticker is attached on the spring, the paper stickers will be observed to vibrate to and fro, or we say it will vibrate forward and backward. The demonstration shows that the vibration of the particles in the spring is parallel to the direction of wave travel. This kind of wave we call longitudinal wave. For a traveling transverse wave, let's consider the displacement distance graph. Before the wave is set up at time 0, the equilibrium position of all the particles lies on this line. Let's consider some particles that are evenly spaced. At time 0, they are A, B, C, D, E, F, G, H, and I. And at time T, the wave strength becomes this one, and assume the wave is traveling to the right. The positions of the particles will become A, B, C, D, E, F, G, H, and I. Since the wave is traveling to the right, therefore, at that instant t, the particles that are moving upwards are D, E, F, while the particles that are moving downwards are A, B, H, and I. While the particles that are instantaneous at rest are C and G. And for the displacement, particles A, B, C, D have positive displacement, while particles F, G, H have negative displacement, and particles A, E, and I have zero displacement. For traveling longitudinal wave, let's consider before the wave is set up at time equal to 0, the respective positions of some evenly spaced particles are A, B, C, D, E, F, G, H, and I. assume that the wave is traveling to the right. For a longitudinal wave, the particles are vibrating in a directions parallel to the direction of travel of the wave. That is, the particles are vibrating forward and backward. By comparing with the displacement distance graph of a transverse wave, we can find that the respective positions of the particles at time t will be A, B, C, D, E, F, G, H, and I. For a transverse wave, the amplitude is A. For a longitudinal wave, the amplitude is A. For a transverse wave, we have crest and trough. For a longitudinal wave, we have E is the position of compression, while A and I are positions of wear fractions. By using the convention of the coordinate axis, we can deduce that the particles for a longitudinal wave at time t that are moving to the right are D, E, and F, and the particles that are moving to the left at that instance is A, B, H, and I, and the particles that are instantaneous at rest are C and G. For transverse wave, the wavelength is the distance between A and I. Similarly, for a longitudinal wave, the wavelength is the distance between successive wear fractions or successive compressions. Let's check your concept now. At the top, you see the respective positions or the equilibrium positions of some particles A to M that are evenly spaced. And now a longitudinal wave is set up towards the right, and the displacement position graph of the particles at time t is shown on the graph. Can you draw the actual positions of the particles from A to M at time t? First, at time t, particles A, C, E, G, I, K, M have zero displacement. That means A, C, E, G, I, K, and M are at their equilibrium position, while particles B, F, J have vector displacement with amplitude with positive value. That means the particles B, F, and J have vector displacement towards the right from their equilibrium positions. And this is amplitude. For particles D, H, L, they are at their vector displacements with negative value, and this is also amplitude. Therefore, these particles for a longitudinal wave have vector displacement towards the left from their equilibrium position. That means this is D, H, and L with amplitude here is A, this is A. Hence, we can find positions of compression C and position of rarefactions R, and the wavelength is the distance between successive compressions or distance between successive rarefaction lambda. Let's look at this example. The graph shows the displacement distance graph of a longitudinal wave that is traveling to the right at a certain time instance for particles from 0 to 12. Can you find which particles are at the center of compressions and rarefactions? And can you find the amplitude and wavelength of the wave? From the information in the last page, you see that particles 0 and 12 are at centers of compression, and particles 6 is at center of rarefaction, and the amplitude of the wave A from the table is 1.2 cm, and the wavelength of the wave is the distance between successive compressions, which is equal to 12 cm. First, look at the question. First, let's draw the positions of rarefactions R and position of compressions C. Then we can draw the displacement distance graph. The particles that are at rest are 3, 7, and 11. And the particles that are moving to the left are 1, 2, 8, 9, and 10. And particles that are moving to the right are 4, 5, 6, and 12. And the amplitude is A, and the wavelength is lambda.